In section 5.5, we're going to look at complex eigenvalues. So the idea here is that sometimes those characteristic equations, when we find the eigenvalues, obviously they have to be solutions of polynomial equations, but sometimes solutions to polynomial equations can be complex numbers. So let's take a look, and I want you to push pause on the video and calculate, using the characteristic equation, the eigenvalues for matrix A. Okay, so when you go ahead and do that, we take this A minus lambda I is negative lambda 1, negative 1, negative lambda. When I take the determinant of that, I get negative lambda times negative lambda. That's going to be a positive lambda squared, minus negative 1 times 1. That's minus negative 1. So I get my determinant to be lambda squared plus 1. That means the characteristic equation is lambda squared plus 1 is equal to 0, which does not factor over the real numbers. But it does factor over the complex numbers. If I'm okay with using complex numbers, then I can factor this as lambda minus I and lambda plus I. By the way, you can also solve this by using the quadratic equation. Let me input the quadratic equation. Go. Quadratic equation is opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Let me erase this real quick. And if you remember back what that is, what that stands for, those are going to be solutions to this equation as long as we can write it as a lambda squared plus b times lambda plus c equals 0. Okay, so as long as we can write an equation like that. Now, obviously, in my case, I had a 1 for A, a 1 for C, and B was 0. So that quadratic equation turned out to be, again, B is 0. So 0 there. Whoops. 0 in for B. A and C are both 1. And if you go through and simplify that, you get 0 plus or minus square root of 4, or excuse me, square root of negative 4 divided by 2. I don't think, let's see if we can do this. Sorry for the delay. Square root of negative 4 is just negative 1 inside the square root. Factor out a 2. And obviously, we get a square root of negative 1. 2's will cancel. Dividing by 1 doesn't do anything. So what we end up with is plus or minus the square root of negative 1, which we know is a complex number, right? We get plus or minus I. So if you're not really good at factoring over the complex numbers, you can always use this quadratic equation and solve that and come up with your solutions, which are complex numbers, if we have complex numbers. By the way, in all the previous sections we did, we had nice characteristic equations, so they could all be factored fairly nicely. But when in doubt, use the quadratic equation. Now, all of that's to say that this matrix A has complex eigenvalues. Now, if we're doing this over the real numbers, then we're kind of out of luck. Over the real numbers, the matrix A would not have any eigenvalues. But if we allow complex numbers instead of real numbers, then everything kind of works out fine. Now, the reason that this is true, the reason that a matrix with real number entries may lead to a characteristic equation which has solutions which are complex numbers is simply the fact that some polynomial equations have complex number solutions. So some polynomial equations have complex number solutions, and therefore, when we're calculating our eigenvalues, sometimes those eigenvalues can come up as complex numbers. Now, like I said, if we allow ourselves to use complex numbers, and if we allow ourselves to use not only complex numbered entries into our vectors, but also complex numbers constants when I multiply, then everything kind of works out fine. And I can find eigenvalues, which are complex numbers. I can find eigenvectors as well when I do that. In fact, let's take a look, at my previous problem that I was doing. Obviously, what we did is we found I and negative I as my eigenvalues. So let's try to find an eigenvector that's associated with the eigenvalue of I. All right? So we're going to do the standard thing. We're going to take A minus lambda times the identity matrix. And just plug in I. So this is just A minus the complex number I times the identity matrix I is going to be equal to negative I, 1, negative 1, negative I. Now you may think, well, shoot, how are we going to row reduce this? We're going to put this into row reduced echelon form. We're going to have to do it by hand because our calculators don't deal with complex numbers very nicely. But that's okay. It's not too terrible. Once you see this done once, then we can do that. All right, so here's how I would row reduce. The first thing is I'd try to get rid of this negative 1 here. If you multiply this top row by I, and then add to that second row, then I times negative I gives me a positive 1. I times 1 gives me an I. Add to this bottom row. Hopefully everybody understands what I'm saying there. Let me adjust this slightly. So what I'm doing is I'm taking the complex number I, multiplying it by that first row, adding to the second row, and replacing. Okay, when you do that, I times negative I gives you a positive 1. Add, you get 0. I times 1 just gives me I. Add, you're going to get 0. So what happens is that this ends up as the matrix negative I, 1, 0, 0. Oh, I shouldn't have said that. I apologize. In my first row reduction step. All right. So in my first row reduction step, I get that. Now next, well, how am I going to get this to be a pivot point? I just have to multiply this top row by I. And therefore, I times this is going to be 1. I times 1 is going to be I. So we're going to get the following matrix. So there we go. So I just set that up. We're row reducing A minus complex number I times identity matrix I. Step 1, I showed. Step 2, we get that. And what's that mean? That means that we have an eigenvector of, what would I need? Well, x1 is going to be negative I times x2, and x2 is going to be free. So the eigenvector we're coming up with is negative I1. Okay? Now again, we do that by hand. It takes a little bit of time, but this one is not so crazy hard. You can do the same thing with a negative I. You could row reduced by hand. Turns out the eigenvector I believe you get for that is I1, so positive I1 when you go with negative I. So all of that is just to say that yes, we can get complex eigenvalues, and yes, when I do that, my eigenvectors can also come out to be complex. And by complex, I mean having complex entries. So what I'd like you to do is I'd like you to calculate the eigenvalues for the following matrix, and then try to find an eigenvector corresponding to each eigenvalue. Go ahead and push pause on the video and do that. All right, so we're going to take a look at this one, and we're going to go through and do this. So you go A minus lambda I, pretty straightforward, create this. You can see what's going to happen when I take the determinant. 3 minus lambda is going to be multiplied by negative 3 minus lambda. When that's all said and done, you're going to get a negative 9 plus lambda squared. Your middle terms are going to cancel out, so you're going to get lambda squared minus 9. And then we're going to do minus 9 times negative 2, so that's minus negative 18, which is the same as adding 18. So negative 9 plus 18 becomes 9. We get lambda squared plus 9 equals 0. Now, if you want to use a quadratic formula, go ahead. Again, be a 0. You can do that. But this one you can also just hopefully see that to square and add 9 and get 0, you have to either plug in a 3 times the complex number I, or a negative 3 times the complex number I. So those are my two eigenvalues for the matrix. Now the eigenvectors take a while to calculate, all right? It's kind of nasty. There's kind of some ugly complex numbers lying around, but it is doable if you have the time and patience. So let's take lambda equals 3I. So you take A minus complex number I times the identity matrix I, and you get this matrix here. So we just subtract 3I from both the 1, 1 entry and the 2, 2 entry. Now, we're going to row reduce that. I row reduce that by hand. My calculator doesn't do that very well. Now it's a little bit tricky to go from here and zero out these rows. One way to do it is ask yourself, what do you need to multiply by -2 to add to get this one? So a lot of times we think of it as the 1, 1 entry, trying to add and eliminate this entry 9. But hopefully when we have an eigenvalue, this is going to give me a solution to the homogeneous matrix equation, ax equal, or excuse me, a minus I equals times x equals 0. So we know we're going to get a row of zeros. So all I'm saying is ask yourself how to go from -2 to this. What you'll find out is that you'll have to multiply that first row by 1.5 plus 1.5i. And then once you do that, add it, and you'll get a row of zeros. Or, I'm sorry, I apologize. So negative 1.5 minus 1.5i. I looked at my notes there. So again, it's an ugly thing, but that's what you do. And then in order to get a 1 in this entry, it turns out you'd have to multiply that first row by a 1/6 plus 1/6 times I. And if you do that, you get the matrix 1, this complex number, and then 0, 0. So that is the row reduced echelon form of that matrix. Now, once we have the row reduced echelon form of that matrix, we can find an eigenvector. X1 has to be positive 1/3 plus 1/3 I. X2 is free. So the eigenvector is this one. Now it turns out that if you do the same process using -3i, a, minus -3i, which is like plus 3i. You know what I just realized? I just realized that I had minus I and I should have had minus 3i in both spots. My apologies. Minus 3i, minus 3i. So here we go, a plus 3i. So you add 3i to the 1, 1 and the 2, 2 entries. You row reduce in a very, very similar way. And you'll get out a row reduced echelon form that is 1, negative 1/3 plus 1/3 I, and then 0, 0. By the way, you're multiplying this first row by a negative 1.5 minus 1.5i. So let me just write that down. So you're multiplying that first row by a negative 1.5 plus 1.5i. And then when you multiply that times the top row, add it to the bottom, that's how you get the 0, 0 entries. And then when you multiply this one, it's going to be very similar. We're going to go 1/6 minus 1/6 I. All right. So let's just write that down. 1/6 minus 1/6 I. That'll give you a 1 in this entry and a negative 1/3 plus a third I in this entry. So when we take our A plus 3I times our identity matrix and row reduce it, we get this thing, which gives me an eigenvector, which is 1/3 minus a third I, 1. Now, that was a really long, it took a really long time to find eigenvectors there, but the eigenvalues kind of jumped out to us, the complex eigenvalues. So that's what we're going to focus on in the next example. All right, I want you to find the eigenvalues here. It says then find the eigenvector, but we're going to ignore that for purposes of time. Let's just find the eigenvalues for this matrix A. So go ahead, push pause on the video, find the eigenvalues, and then we'll sort of leave off the eigenvectors right now. Okay, so hopefully you did that and got the answers. Let me go through this, what I did. So we take A minus lambda I, we get 8 minus lambda, 9, negative 5, negative 4 minus lambda. We calculate the determinant of that. So 8 minus lambda times negative 4 minus lambda. All right. You end up with, sorry, that should be lambda squared minus 4 plus 13 equal, and so that's the determinant, right? Lambda squared minus 4 lambda plus 13. So the characteristic equation is that determinant is equal to 0. When you do this, I chose to utilize the quadratic formula. And when I did that, middle term here, negative 4 is my B, 1 is my A, 13 is my C. So opposite of B would be a positive 4 plus or minus negative 4 quantity squared minus 4 times 1 times 13, all divided by 2 times 1. So that's what I went ahead and did. Whoops. 4 plus or minus square root of negative 4 squared minus 4 times 1 times 13 all over 2 times 1. Now 2 times 1 is 2. This thing underneath the radical calculates out to be a negative 36. Now if we're going to take the square root of negative 36, well, 36 is 6 times 6. Negative, so I factor out the 36, square root of 36 is 6. Factor out a negative 1. Square root of negative 1 is what we call I. So my eigenvalues are 2 plus 3i and 2 minus 3i. Okay, that's after I divide that by 2. So we get those as eigenvalues. Now you can imagine that it's going to be a little bit complex. It's going to, no pun intended, to put those two eigenvalues in here and then row reduce by hand. You can obviously do it. It just takes a little bit of time and effort that I don't really want to spend on this section. So there are the eigenvalues. I want you to try this one on your own too. Just find the eigenvalues. Don't worry about finding the eigenvectors corresponding to those values. We know we can do it. we also know that it would take some time. So just find the eigenvalues and then you're good. Push pause on the video and try this problem. So what I did when I did this, same as we always do, a minus lambda I, find the determinant. You can push pause if you'd like to slow this thing down to check that I've done my matrix correctly. I believe I have 1, 4, negative 4, 1. So a minus lambda I, 1 minus lambda in the 1, 1 spot, 4 in the 1, 2 spot, negative 4 in the 2, 1 spot, 1 minus lambda in the 2, 2 spot. I take 1 minus lambda times 1 minus lambda minus negative 4 times 4. So 1 minus lambda times 1 minus lambda minus negative 4 times 4, that's a positive 16. When you multiply this out, lambda times lambda gives you lambda squared. 1 times minus lambda, another 1 times minus lambda gives you minus 2 lambda. You get 1 times 1 plus 16 gives you a total 17. So we end up with lambda squared minus 2 lambda plus 17 is equal to 0. If you can think through factoring that, by all means, try to think through factoring that. Most of us won't be able to do that. Most of us will have to rely on a quadratic equation. So opposite of b plus or minus square root of b squared minus 4ac, all divided by 2a. By the way, in this case, my letter b here is the negative 2. My a is the number 1, and my c is the number 17. So we get opposite of negative 2 is a positive 2, plus or minus the square root, b squared, negative 2 squared minus 4 times 1 times 17, all divided by 2 times 1. 2, this 2 doesn't change, plus or minus the square root. If you simplify inside that square root, you get a negative 64. Square root of negative 64 is 8i. And so you get 2 plus or minus 8i over 2. When I do the plus and then simplify, I get 1 plus 4i. When I do the minus and simplify, I get 1 minus 4i. All right? So hopefully that all came to you. You might need a little bit of dusting off of the quadratic formula, but that's pretty much it for finding eigenvalues. Obviously, when we find eigenvectors, like we did in this very first one, sometimes the eigenvectors are fairly complicated. And we could have done that for our last two examples, but I just chose not to. I thought it takes enough time just to find the eigenvalues. We don't need to spend trivial time finding the eigenvectors. All right, at least not right now. By the way, the other thing you should notice about these eigenvalues is that they're always popping up in pairs. So notice this eigenvalue was 1 plus 4 times the identity. Or excuse me, not 4 times the identity. 1 plus 4 times the complex number I. This one is 1 minus 4 times the complex number I. In our previous problem, the eigenvalues we got were 2 plus 3i and 2 minus 3i. If you look at the eigenvalues in our example we did with the 3, -2, 9, -3 matrix, I got 3i and -3i. By the way, this could be thought of as 0 plus 3i, 0 minus 3i. So what I'm saying is, we should notice that if a polynomial equation, which has real number coefficients, ends up having complex solutions, then they have to occur in pairs, specifically what we call conjugate pairs. So if one is a plus bi, the other is a minus bi, where the a and b are just real numbers. So if you had 7 plus 8i as an eigenvalue, you would also have to have 7 minus 8i as an eigenvalue, just because we know how to solve equations with real number solutions. All right, so hopefully that all makes sense. This is a pretty short section, and this ends chapter 5. As always, if you do have any questions, come see me in my office hours.